Okay, why don't we start? So I'm Mike Douglas, and this is the New Technologies in Mathematics seminar series of the CMSA. And this week we're delighted to have Yamini Bansal and Boaz Barak tell us why understanding generalization requires rethinking deep learning. In fact, the title, which is twice as long, but you can read it or I'll let them explain it. Our custom is that during the talk, feel free to ask questions. And the best way to do it is to put it up on the chat box. And then we'll either invite you at the appropriate moment or save the question a bit. And then at the end of the talk, there'll be a few minutes for open questions. So without further ado, Yamini and Boaz.
Hi everyone, and yes, so yes, thank you so much for this invitation. So Yamini and I will give this talk. I will start with the fluff, the introduction, etc., and then Yamini will actually show the meat of the talk, or the if you're a vegetarian, the beans of the talk. And this is joint work with Gal Kaplun, another wonderful student here at Harvard. So the technical title of the talk is Generalization Bounds for Rational Self-Supervised Learning Algorithms, and it has a lot of technical terms, which I hope will become clear. And the non-technical version is Understanding Generalization Requires Rethinking Deep Learning with a question mark, and I hope that will also become clear this interpretation. Okay, so the object of this talk is supervised learning. What is supervised learning? We can think of it very abstractly for this talk as just a black box, which we think of as a training procedure. And this black box gets as input data. For example, it gets a list of labeled samples, like an image of many images of dogs and cats with the label dog or cat. And what it outputs is a classifier. What is a classifier? Again, we are thinking abstractly. It's some algorithm that computes some function that when it gets a new image, it can output the label. And hopefully, it will be the correct label. So the goal of a supervised learning algorithm, a supervised learning training procedure, is to get given data to output a classifier that will be successful on future data that it had not yet seen. Okay, and more formally, we think of the data as being x, y. So x is the data points, the domain of the data points, and y is the domains of the labels. And we get the training set is an n-tuple of x's and an n-tuple of y. So x1 till xn and y1 till yn, the labels. And two important quantities are the training accuracy, also sometimes known as empirical loss. This is how well does the classifier that we output performs on the actual data that we have seen. So this is the probability over everything, all of the randomness in this experiment, and in particular, maybe the most important is the probability over a training sample, or so over I chosen from 1 to n, the probability that the classifier outputs the correct value on the classifier outputs the correct value on this training sample. And then there is the population loss, so 1 minus the population loss, or the test accuracy, which is the probability that the classifier output will output the correct value on a fresh xy coming from the unknown test distribution. And one of the main questions we want to ask, we want to answer in learning theory and in learning in general, is what does the former quantity has to say about the latter? And this is, of course, the general question we always ask in statistics. What does an empirical quantity say about the population quantity? And this is known as the generalization gap. And so this is the training minus test, and hopefully we would like this to go to 0 as the number of samples goes to infinity. Doesn't always work this way, but this is what we would like to happen. So what do people do in practice these days? How do they solve supervised learning? So the current state of art and current method of choice is end-to-end supervised training of deep neural networks. What do we mean by this? The idea is the following. You get this training set, this collection of images of, say, cats and dogs, and they are labeled as cats and dogs. And basically, a deep neural network, we can think of it as a very complex curve. It's just curve fitting. So we take a very, very complex network, which by complex, I mean it has many, many parameters. And we just fit the data. We think of it as passing in high dimensions. You can think of it as some kind of a complex high dimensional surface that separates out where the cats will be on this side and the dogs will be on the other side. And this is basically what training does. So training finds the parameter. So we fix some architecture which determines. Was there a question?
There's a bit of echo. Somebody may not be muted.
Okay. So if someone has a question, I'd be very happy to answer. So what we do is simply the training algorithm finds these parameters that make sure that all the cats fall on one side of the curve and all the dogs fall on the other side. And for future samples, if they fall on the dog side, we will say that they are dogs, and if they fall on the cat side, we will say that they are dogs. And this actually does very well in practice. So generally speaking, the bigger the parameters, this is not necessarily the ultimate best. These things keep changing every month. There would be a new neural net that does even better than the one before, and probably is only bigger and more complex than the one before. But generally, these are just some examples. They do very, very well. So what you can see is that this is the test accuracy. So they perform very well. They manage to succeed in classifying correctly. This is on CFAR10. This is a data set that contains not just dogs and cats, but generally 10 categories. Dogs and cats are 2 of them. And they do very well. They succeed in the vast majority of samples. And another thing that a curious aspect of this table, you can see that the train accuracy is 100%. That means that you can actually always fit a curve that makes all the dogs in one side and all the cats in another. So for the training set, you get 100%. You find the curve that can fit everything, that can put everything. And for the test, you get not 100%, but you get pretty good. And now, in 2017, Zhang et al. Performed a very interesting experiment. They considered the same distribution, say CFAR10, but they considered the case that where instead of the label being the right label, it's just a random label. There are 10 classes, so just a random number between 1 and 10. If the label is completely random, then test success will be 10% because you really cannot guess better than chance. But what they were wondering is what would happen to train success. And surprisingly, or maybe not surprisingly, they found out that train success is still 100%. So basically, not only you don't get a generalization gap that goes to 0, the generalization gap can actually be as large as possibly can. It can, so training performance is completely non-informative metric. It can be 100% and it will tell you nothing about how you will perform on future samples.
Boaz, can I ask you something really simplistic?
Yes, of course.
So, and no imposition here on the size of the classifier, right? It could be exactly the size of the data set.
it could be much bigger even. It usually is. It usually is.
So in other words, what's the surprise? Why don't you just have a table with all the answers?
Yeah, I mean, it's not surprising. I mean, you can ask. There are like two versions of surprise, right? You could either be surprised by this, or by this, right? So you could either find it surprising that given that it could have been a simple table that would get 100% but would be meaningless on things that you haven't seen, that you could either be surprised that it does so well in the first table on things that it hasn't seen. So that suggests that what's going on, even though you have a lot of numbers, you're not simply building a lookup table. And given that you're not simply building a lookup table, then you might think that if you were given completely random thing, maybe it will not get 100%, but they showed you actually do get 100%. Okay. So in some sense, or maybe you're not surprised at both, but in some sense, what they showed is that the training success is not informative for the test success. The test success could be very high or it could be very low, and the training will still be 100%. And indeed, but you're absolutely right. Because you have more numbers than data points, maybe it's not surprising you can achieve 100%. So basically, the bottom line here is that supervised deep learning works great in practice, but the training accuracy on its own is not informative. And this is unlike the kind of usual philosophy of classical learning theory. So that kind of rules out the dream, right? So maybe we had this dream of, that basically we'll get something like a test minus train is some quantity that goes to zero, and goes to zero in a sense that not just to infinity, but also in parameters that we can actually see in practice. And Zhang et al. Basically say, this is what happens in classical learning theory, where you usually don't use more parameters than the size of the set. And, or maybe you could have hoped that maybe somehow the algorithm effectively uses less parameters. And basically Zhang et al. Said, no, forget about this dream. Then if you want to understand deep learning, you need to rethink how you do generalization. This notion of generalization gap from classical learning theory does not apply for deep neural network. We need to do something else, because deep neural network generalization gap could be as large as possible. So you need to do something completely different. And what we show in this work is we take algorithms that are still deep neural networks, but are used in a different way, which we will define, but we call them self-supervised plus simple. And these are algorithms that practitioners have started to really like in the last few years. And this is not a paradigm that we invented, and no, we didn't also invent any algorithms. So these are algorithms that practitioners have been using, and they have shown in the last few years that they actually work great. Right now, they still don't achieve the state of the art, but they get pretty close to whatever you can get with supervised training. So it was known that they work great. But what we show is that the generalization gap is actually good, and we can actually even prove that it's small. So in some sense, maybe the problem wasn't with generalization. Maybe the problem is that we just needed to do deep learning a little bit differently. So if we just do deep learning a little bit differently, which practitioners have their own reasons to do regardless, then maybe we can go back to the dream. We can have generalization gaps that both asymptotically tend to zero and actually are meaningful in practical setting of parameters.
Can I ask real quick?
Yes.
So when they added the noise to that task, did that noise just totally overwhelm the signal, or how do you know that you're not just completely overwhelming the signal, so that even like a linear fit would do terrible?
No, they overwhelmed, they had added 100% noise. So it definitely did overwhelm the signal. So that's what I said, like it was obvious that the test probability, the test success would be 10%, but if you add the linear classifier, then the training would have been 10% as well.
I see.
So what they showed is that basically you might have thought that maybe even though you could have had these theories that even though you're using tons of parameters, maybe the algorithms that you're running are not actually using all these parameters. Maybe the true capacity of the network is much smaller than the number of parameters would indicate. And what Zhang et al. Showed, this is not the case. The algorithm actually has the capacity. There is the capacity to fit the data completely, even if the labels are completely random.
Okay.
Can I ask a quick question? So, like in this semi-supervised setting, what do you see if there are random, like if you do the same experiment with random labels, do you get zero training error or no?
We'll see that actually maybe in the next slide. So, so we'll see exactly that. So yeah, and there are like been some other works on trying to analyze special cases of these kind of SSS algorithms and under certain statistical assumptions, and it would be a little bit too much of a detour to explain both these special cases and both the statistical assumptions. So I'll just put a reference here and people can look it up or ask me about this in the Q&A. Okay, so I'll first describe what SSS algorithms are, and I'll show exactly the experiment you ask soon, I think in the slide, maybe after this one. Okay, or maybe a couple of slides ahead. Yes, so what are self-supervised but simple algorithms? So the name is new, the concept is very old, so we call it SSS algorithms, and to motivate it, we consider the difference between how we describe neural networks learn and how humans learn. How does a baby learn? So how does a baby learn how to classify between dogs and cats? So a baby will typically not get a bunch of labeled examples. Most of the images that the baby sees, you know, in the first year or two of their life do not come with explicit labels. So the baby kind of observes all these unlabeled images. And to some extent, we can think that these unlabeled images were even observed during evolution. So the human brain has evolved to be a good, to have a good internal representation of the images that we tend to see. And then you typically don't have to show many examples. Maybe you only show one example. You show a baby a single picture of a cat. You say, okay, this is a cat. You show a single picture of a dog. You say, this is a dog. And from then on, often they will know, even if they see cats and dogs that don't look at all like the ones that you've seen, that they often will be able to classify the two. So, so babies tend to maybe see many unlabeled images and very few labeled ones, and still be able to successfully classify. And the idea behind self-supervision is somehow to try to do something that is a little bit more similar to how humans are doing things. So an SSS algorithm starts off with getting a lot of unlabeled images, and then it uses that to learn a complex representation. So a representation is still a neural net, but now it's not a neural net that outputs a label. It doesn't output cat or dog. What it does is output some representation. So, so it still has many, many parameters, more parameters than the number of images, and etc. But what it does is really just maps the input into representation space. And the hope is that if you're learning the representation, a good representation, then it will actually be a meaningful one. For example, it will make the dogs and the cats linearly separable. And once they are linearly separable, you can use a very simple classifier. For example, a linear classifier, or generally another simple classifier to separate out the dogs and the cats. So the idea is that you work in two stages. First stage, you learn a representation without using the labels. And then in the second stage, you use the labels to fit a very simple classifier on top of this representation. But the overall model that you get is the composition of the simple classifier and the representation. So it's still a very complex model, but you just learn it in two stages. So let me try to make this more formal. So an SSS algorithm is composed of two training procedures. So first step, it gets the data only without labels, and it outputs a representation. So this is sum up from X to R to capital R, which is this representation space. And then the second stage gets as input the labels. So this is only data. And this is the representation of the data plus the labels. And then it outputs a simple classifier. So this will be complex. We'll have many parameters. This will be simple. We think of this as having fewer parameters than the number of points. And the final classifier is f of x is g of r of x. So one way to think of an SSS algorithm is we can think of it as just a special case of a training procedure that just think of it as a black box. It gets data and labels, but just uses them in this particular way to obtain the final classifier. So rather than fitting a complex curve directly, it first finds the representation and then fits a simple curve on top of it.
You'll tell us how to train that first stage now?
So I will not tell you how to train it because this is what practitioners have done this, right? So these are, practitioners have found several ways to do that. And we basically treat it as a black box. So I can tell you just for curiosity that there are two main approaches that people currently use. So the first approach is reconstruction. So the idea would be that maybe you define, maybe you give the images and you block out some part of it, and then you try to train a neural network to reconstruct the part that you blocked out, and use the internal layers of this neural network as some representation. A second approach is known as contrastive learning, where you take an image and you apply some operation to it that preserves its meaning. For example, you change the coloring or you shift it around or something like that. And then you try to find a representation that makes the images that have been came from the same original image close to each other in Euclidean space, and the images that did not far from each other. Yeah. So obviously, the smarter you are about this step, the better the representation, the better your performance will be. In this work, we are mostly concerned not with the performance per self, but rather with the gap between the trained performance and the test performance. So we'll kind of show that the gap is small, but of course, you don't want just the gap to be small. You also want, in practice, you also want the train to be high. It's not enough that the gap is small.
So Boaz, just to check. So the output of R is what R would have predicted on X, and plus the correct label.
No, so R doesn't try to think of labels, right? So R, no, so R actually, R you can think of it like if we are like not abstract, let's suppose that, X is some pixel. So we think of X as saying R to the, I don't know, D. So R of X will just be some high dimensional representation. So we can think of it as R to some, I don't know, L. So it's just some high dimensional vector. It doesn't know, R doesn't know the label. So it doesn't try to predict if it's cats or dogs. But if you found a nice representation, like a high level representation, it might be naturally that semantic classes will become linearly separable, but you're not explicitly trying to do it. So R itself doesn't contain label information. It's just representation.
And then you add on to it the two labels, and you run it through this. And where's T-fit coming from? That's something you design?
Yeah, so you design a T-fit, which basically, so maybe the example to think in mind is that you just fit a linear classifier. So basically, if you try to directly find a linear classifier between dogs and cats on pixel space, you are doomed, right? Mm-hmm. But if you are doing it in a nice representation space, you can actually do it. Mm-hmm. So you're trying to learn the representation, and yeah, and I think I see Yamini in the chat also mentioned some other types of pretext tasks. But maybe maybe in a kind of a simple, if you haven't seen this before, maybe a simple example to think of is that in the first thing you're trying to predict one half of the image from the other. And that kind of forces you to find a nice representation. So, and then you just output, you forget about this task. It was, you just use the intermediate representation that you came up with in the performance of this task. And now you get the labels and you just fit a linear classifier and you hope that this actually works now.
Okay, thanks.
Okay. So, here is how they do on CIFAR 10, and what you can actually see is that they do actually pretty well. So when you do these SSS algorithms, generally speaking, if you use the same architecture of neural networks, so if you use you take the same neural networks that you would use for supervised training and you use that for the representation, then I think right now, Yamini is much more of an expert than me, so she can chime in, but I think right now you'll be probably maybe 1 or 2% worse than what you get from supervised training. Yamini, is that correct?
Yeah, that's correct.
Yes. And what's interesting here is that this is not 100%. And it's kind of not obvious because you do have, the final classifier you output is a classifier that has many more parameters than the number of data points. And it does depend on all the data points. And there is also no, I mean, it's true that y is only arrives here, but notice that y is not independent of x. That probably, you know, the entropy of y condition on x is probably 0. You know, if you have seen the pixels, there is no entropy in terms of like whether it's a cat or a dog. So in some sense, the representation has many parameters, and it depends on all the information in the data. So it's kind of maybe not obvious. Yes.
There's like an implicit selection going on here, because it could also have been first stages which didn't work with the classifier, and then people wouldn't report those, right? You're telling us the ones that work, and how do we know that you know, some equally plausible looking first stage might not work?
Yes, no, that's true. That, I mean, I think maybe, but the thing is that there is something that does work. That's nice. That there is something that actually succeeds, that gets very good levels with this type of framework. That this framework is not, I mean, it's not a framework that somehow is obviously inferior to, and it has a lot of practical advantages. For example, if you have tons of unlabeled data, in this framework, you can actually use it. When you're doing supervised learning, then you don't know what to do with it. So there are like some practical, the reason that practitioners like this framework is not because of generalization gap. I don't think they even observe that it has small generalization gap, but because of some other advantages. But it's nice that it actually does get good test. And it's not obvious, it's not a priori obvious, but train is not 100%. And now let me mention exactly what Pritish asked. We actually ran the Zhang et al. Experiment on this architecture. So this is with 100% noise. So this is not surprising. 10% obviously, 100%, you know, 90% noise. 90% of the things are just wrong, and 10% are by chance the same. Then obviously you'll not be able to succeed better than chance. But what you see is that actually this is small, right? So you see that there is actually train is informative. It is indicative of test. So these type of algorithms, then they do actually train is indicative of test. And in fact, we decided to interpolate between the two things. So we said, let's try and see what happens as we gradually increase the noise. And what we see is the following. So as you increase the noise on the left side, these are kind of supervised algorithms, classic end-to-end supervised, and these are SSS. So as you increase the noise in the supervised algorithms, training stays stuck at 100%, and just test becomes worse and worse and worse. In these SSS algorithms, as you increase the noise, they go together. So the training actually tells you what is the test. And you can see that the actual test, it's not as if the left performs much better than the right. The left and the right kind of perform similarly, but the right training tells you much more information about the test. So at least the Zhang's et al. Observation do not apply to these SSS algorithms. We do have a fighting chance at a small generalization gap. And basically this paper is about, okay, we have a fighting chance at proving it, but can we actually prove it? And that's basically the point. So basically our results in a nutshell are the following. So we first showed that for any training algorithm, and it doesn't matter if it's an end-to-end supervised algorithm or an SSS algorithm or something else, every training algorithm, we can upper bound generalization by 3 quantities, which you will see the definitions, which we call robustness, rationality, and memorization, and we call this the RRM bound. So this is really an observation, just as you'll see, but it's a useful one. And then what we show, we give some evidence, and there is some theoretical evidence and empirical evidence that in practice, whether you are end-to-end supervised or you're using SSS, the first 2 quantities will always be near 0. So they will always be small. So the lion's share of generalization gap really comes from the third quantity. So this is the part that plays the big role, the memorization. And then we give a theorem that proves that for SSS algorithms, memorization is bounded by a quantity which is like the complexity of the single classifier, the square root of the complexity of the simple classifier divided by n. And complexity, in the paper, we define the more refined notion of complexity. For this talk, just think of it as the number of bits to specify the simple classifier. But the crucial point is that this is completely independent of the number of parameters or bits to specify the representation. The representation can be arbitrarily complex, but this, as long as the complexity is smaller than n, then this can actually go to 0 when n goes to infinity. So we can actually have these bounds that go to 0. And the fourth thing is that we show that, and then we actually use this, our more refined notion of complexity that is in the paper, that in practice, this bound actually is small enough to give meaningful bounds. So the bounds are not tight, but they are not vacuous. And not vacuous might seem like a low bar, but it actually is not. Like it's very hard in deep learning to get non-vacuous bounds. So yes, so it is actually nice. And yeah, so now basically that I've finished saying what we'll do, let's actually get to the person that knows how to do it. So let Yamini continue.
Okay, thank you, Boaz. Let's see if.
Okay, so let's see if I can stop sharing and then you can start.
Okay. Okay, somebody's calling me at the wrong time. Sorry about this.
Yes, that's always with Zoom. There we have like new experiences in the possible ways. We used to fight with projectors in auditorium halls. Now we get different things to fight with.
Yeah, and somebody is trying to offer me a stay at the Marriott Hotel, so that's kind of interfering with the presentation right now. All right, well, thank you, Boaz, for a really nice overview of our work. What I'm going to do is I'm going to get into all the details of what all of these terms mean. So I'll start by defining generalization, robustness, rationality, and memorization. And then we'll try to do a quick sketch of how we get that this memorization gap is bounded. And then we'll see how all of this comes together in practice and what this tells us about what's going on in algorithms that practitioners actually use. Okay, and please feel free to stop me if anything is unclear, especially because there's going to be a little bit of notation in what we're going to see now. Cool, so let's start with the generalization gap. Just as a quick recap, we get as an input some data XY in XY pairs. We have some training algorithm, which spits out a classifier F. And we're interested in bounding the generalization gap of this classifier F. And what is the generalization gap? That is the difference between the train accuracy and the test accuracy. So if you select a train point at random in your train set, what is the probability that you make the correct prediction for it? Versus if you receive a fresh test point X, what is the probability that you make the correct prediction for it? And for most of what we're talking about, we'll be dealing in accuracies and in percentages. So both these quantities will lie on this 0 to 100 line. And this in between is the generalization gap. And for the terms that appeared in the previous slide, robustness, rationality, and memorization, we're going to conduct a reference experiment. So this reference experiment is identical to the original experiment. So let's say you have some algorithm. We will conduct the original experiment with the original data, but we'll also conduct an experiment that has 5% label noise. And what that means is with some probability eta, we will give some of the points the wrong labels deliberately. And for the remaining 1 minus eta, they will have the correct labels. And keep in mind that this is only for defining the quantities. We are actually going to be bounding the generalization gap of the clean experiment. Okay, any questions about what we're doing here empirically? Cool. Okay.
So for theorists in the audience, think of it as a mental experiment.
Yeah, it's a mental experiment, but we also actually do the experiments. Great. So now we're ready to start defining the quantities. So the first one is the robustness gap. This is not to be confused with other robustness in machine learning. Robustness has come up many times, but
can I ask something, Yami? So when you have 95% of being correct, a correct label and 5% of not, so it's a 0-1 label, or is this extendable to?
No, it's extendable to multi-class. It only says that it should not, when you add the noise, it should definitely be the wrong label. So if your original label was 0 and you had 10 classes, the wrong label must be between 1 and 9.
Got it. Okay.
Okay. So, all right. So with robustness gap, the first quantity that we're going to use with the noisy experiment is this noisy train accuracy. What is this noisy train accuracy? So this noisy train accuracy is just the train accuracy in the noisy experiment. But importantly, we're going to measure this with respect to the correct labels. So we, let's say, did the noisy experiment with 5% noise. That gives us some classifier of f tilde. And we're going to measure the train accuracy of f tilde with respect to the correct labels. So this is telling us that if you perturbed your labels a little bit in the noisy experiment, how much does that affect your training accuracy? Okay, cool. Then the next gap, the next quantity is the memorization gap. And again, this is very similar. The new quantity is similar to the noisy train accuracy. Sorry, is that a question? So this quantity is again the training accuracy, but this time we condition on the noisy points. Okay, so what do I mean by this? Let's take like a simple example. Let's say you had some points, some linearly separable data points. And in my noisy experiment, let's say I mislabeled these points. And I have two classifiers. One of them is the classifier.
I think you should mute your mic.
Yeah, somebody needs to mute.
If you are a host, you probably can mute it for them.
I'm looking through for the, okay, somebody got it, I think.
Problem. Okay, so let's. Okay, can you hear me?
Yes.
Yeah, okay. So let's say we have this data set and I added some 5% noise and this mislabeled some of the samples. And I have two classifiers. I have this one classifier that's just a linear classifier. And I have another really complex one that can make an arbitrarily complicated boundary. And this does something like this. So what happens to the second term for both of these? In the second term, we're conditioning only on the noisy labels. And we're measuring the accuracy with respect to the correct labels. So the second term goes to 0 for the simple class, for the complicated classifier. Does that make sense? But for the simple classifier, it's probably too simple to fit any of the noise. So conditioning on the noise doesn't really do anything. So the probabilities basically remain the same if you condition or you don't condition. And in that case, we will see that this whole term, memorization gap, is kind of close to 0. So this is just an example of how we expect memorization gap to behave. And maybe you can already kind of see how memorization gap will depend on complexity of the classifier that is going to be used later. Okay, and now we have the final term, which is this little gap here, which we're going to call, maybe a little provocatively, the rationality gap. And this gap is the performance difference between the training performance on the noisy points. So again, this is conditioning on the noisy points versus the performance difference on a fresh test point. Okay, so what is this quantity telling us? This is the performance difference when I gave you the incorrect label deliberately versus when I didn't give you any label at all. Okay, and what we will say maybe prescriptively is that if your rationality gap is greater than 0, then you're irrational. So we're saying that if somehow giving you the incorrect label is making you better than having no label, then maybe your algorithm is doing something strange. And why do we say that? Because we have another theorem, the performance on the table theorem, which is stating that if you do in fact have a positive rationality gap, you can transform the training algorithm into one that squeezes out performance from it. And how do we do that? So the intuition is that if no label is better than, if a wrong label is better than no label, then just introduce your test point into your train set with the wrong label. And somehow that should magically increase your probability of doing better. So in some sense, we're saying that if you had a positive rationality gap, you're leaving some performance out. And we know that deep learning practitioners are really good at what they do. So they're probably not doing this. And in fact, we do see that rationality gap is small in practice. Okay, so we have all our quantities. And as you can see on this line here, that when you add up all the quantities I just defined, the terms cancel out and you get the generalization gap. And you might be wondering why there's an inequality here. It's because when we write these three terms, what we actually mean is the max of these with 0. So we only consider these terms if they're positive, and that gives us this inequality. All right, and as Boaz mentioned, this is what we call the RRM bound, and this is just a simple addition and subtraction of terms. It's something that holds for all algorithms, but it might not always be interesting for all algorithms. So we will see next how these quantities actually behave and when they can tell us something interesting about what's going on. All right.
Can you go? Oh, sorry. Yeah. I think that the best, what you're going to do is it's going to be the best illustrator. Go for it.
Okay. Okay. So, okay, let's look at how these gaps behave in practice. So what we're doing here is we took a bunch of algorithms. So there's a whole model zoo of different types of methods. And the blue dots represent all these SSS algorithms with different architectures. And the red points indicate end-to-end sort of training. So what we see is the robustness gap is at most 5%. And I forgot to mention this before, but this kind of makes sense because a robust, an end-to-end classifier can always have 100% training accuracy. So the probability of being correct is 1, and the probability of being correct with noise is 1 minus eta. So this will be eta. Sorry, I'm rushing through it a little bit, but believe me that it works. And in fact, for SSS algorithms, we see that this is always kind of less than 5%. And as I talked about before, the rationality gap is also less than 1%. We did see some extreme cases with ImageNet where it goes up to 4%, but it's small enough that we can kind of not ignore it, but we can assume that it is actually small. And if not, we can convert it to one that is small by doing the expensive procedure that I talked about earlier. And the last thing is the memorization gap. As you can see, the memorization gap actually has some good range. So for a supervised learning algorithm, the memorization gap is high because the boundary is complex and it can fit everything. So it can memorize the noisy labels completely. But SSS algorithms, it's kind of restricted. It goes between 0 and 20, and it depends on details of the algorithm. But kind of the main takeaway is that the memorization gap is relatively small for SSS, and we can actually prove this. So the summary of whatever we defined so far is that the first two are small, or we don't prove this, but we have good reasons to believe that they also should be theoretically. And the memorization gap is large. It forms the lion's share of generalization, and we can actually prove that for SSS algorithms, this is bounded. All right. And as Boaz already kind of hinted, the memorization gap is bounded by the complexity of just a simple classifier. And we'll do a proof sketch of this next. But right, before I do this, any questions about what these quantities are or why we're doing any of this? Now might be a good time.
I had one question. So are you using the same samples for learning the representation as well as training the later classifier, or are these like fresh samples?
No, they are actually reused samples, and that's actually a really good point.
Yeah.
Because that is the thing that makes all of this kind of machinery necessary. Because, okay, let's see. So you have this part of the classifier, which is the representation learning. And this can potentially have lots of parameters. So you can have many, many more parameters than the number of samples. So you can imagine that this part could do something trivial, not trivial, but do something strange, where it might output a good representation for the train set and output nothing for the test set. So in some sense, if you look at the overall complexity of the classifier, the overall classifier is still complex. So if you wanted to think about, like the function class as a whole, it is still pretty complex. And because we are reusing sample, it can memorize the train set. But under our kind of assumptions, that's not happening. I hope that answers it.
Yeah, that's a good point. Yeah, thanks.
Okay, great. So we're ready to now talk about how we get this memorization, how we bound this memorization gap. Okay, so just to restate, the memorization gap is the train accuracy in the noisy experiment. And it's the minus the train accuracy in the noisy experiment conditioned on the noisy points. Okay. All right. Okay, so now to do this proof, we're going to define two random variables. The first random variable A is whether your prediction is correct. So this random variable is over some index that you sampled in your train set, and also over a different noise in your data set in the noisy experiment. And your second random variable B is whether a particular example was noisy. So whether you gave the incorrect label. And now if you stare at this for a second, you will see that the first term here is actually just the expectation of A. And the second term is the expectation of A given B equals 1, right? So what we get is the memorization gap is expectation of A minus expectation of A given B equals 1. And the kind of first step in the proof is that this term is less than the mutual information between A and B.
But this is accounted for in the statement.
Sorry?
Yeah. There is a square root on top of the I, but that's accounted for in the statement.
Oh, yeah. Sorry. Yeah, there is a square root here. Yeah. And we do this using using the Pinsker inequality. I'm not going to get into how we do it, but it's easy to follow in the paper. And the next step is to show that this mutual information is in fact less than the entropy of the classifier. So I'm going to try to sort of show the steps of that. Okay, so the first thing that we do is we just write n times mutual information and expand out the definition, which is HB minus HB given A. Right, and the next step is we expand out the n, so we write it as the sum of these n terms. But now we're going to introduce this conditioning over I. So if you recall, B was over some random index that you picked. And now we're saying that you can write this as a sum with an inequality if you condition also on some sample particularly. And why is this an inequality? Because these two terms are basically equal. B is just a Bernoulli random variable that tells us if you picked noise or no, and they are, it doesn't matter what I and J are, it doesn't matter what your index is, your entropy will always be the same because they're independent variables. And the second term, I'm going to say that because we condition on the index, that can only ever reduce your entropy, because conditioning can reduce your entropy. So this term becomes small, which means that this term overall can potentially become larger. And what this essentially looks like is the mutual information that's conditioned on a particular index. So what we've essentially done here is, earlier we had n times the mutual information where you randomly sample an index. And now we have the sum of mutual information when you pick each index specifically. And we're saying that this is related by this inequality. And the next steps are kind of intuitive. So if you recall, A is whether or not your prediction is correct. So we can swap out A with G because G and I completely determine A. So as with an inequality, we can swap out G. And again, because these are independent random variables, we can say that this will finally be less than the entropy of G. So this kind of completes the proof sketch, and maybe I've rushed a little bit, but things kind of work out. And the complexity that we use in our experiments that we are going to empirically evaluate are kind of mostly closely related to this mutual information. So we'll see kind of how all of this comes together next. Are there any questions about what we're doing here? Okay, great. So now let's see what all of this looks like in practice. So what we've done here is we've taken a bunch of SSS algorithms. So this could be something like a contrastive learning algorithm with a particular ResNet or a convolutional network. And let's say linear classification on top. And each of those variations shows 1 point. And this is just the x equals y line. So this is the generalization gap. Now we first plot the memorization gap. And you can already see that for most of the points, memorization gap kind of forms a lion's share of what's going on. The next is the rationality gap. And the rationality gap is basically 0 for most of the cases. In one extreme case, it's about 4%. And the robustness gap, as we had discussed, is less than 5% in most of the cases. And so this is the empirical RRM bound. And this green line is telling us if we were very tight with our analysis for all the 3 quantities, then this is the bound that we would get on generalization. And if we now replace the orange with the complexity we were discussing previously, then we get these blue dots. And this is our kind of theoretical bound for generalization. And you might see that these are non-vacuous. So these are kind of less than 20-30% in a lot of cases. And maybe that doesn't seem like an achievement, but I think there's a lot of literature in deep learning that's trying to do that for end-to-end supervision, and it's proved kind of hard to do that. But now we're saying that there is some modification of deep learning for which we can get some kind of non-vacuous bounds. And it also seems to, maybe I might be stretching a bit, but it seems to correlate with generalization gaps. So it's not monotonically increasing, but if you ignore a few points, it kind of is. So maybe this is like something that is actually telling us what's going on under the hood with these algorithms. Yeah, so that's about it. This kind of summarizes everything with the paper. And yeah, just the summary and open questions is that these algorithms, practitioners have kind of known that they're good, and now they're starting to get really, really good. And we're kind of saying that whatever the practitioners were doing is right. And this also works in theory. And unlike qualms that people had with end-to-end supervision, that is not true in this case. In open questions, we haven't provided any proper theoretical guarantees for robustness and rationality, but we have some reasons to believe that they should be small. We have some initial indications. For robustness, there's some work with some assumptions. But it's not as general as we initially thought. And finally, Boaz alluded to this before, but we don't really know what is a good representation. So we only talked about gap, but what we might actually care about in practice is gap plus the training accuracy. And in some sense, what are things that you can do that give you good train accuracy with simple classifiers? That's very much an open question. And finally, this is something, this is like an intuition that people have had for some time, which is that supervised learning kind of implicitly does representation learning under the hood in the end-to-end stack. And maybe thinking about it in those terms can help us understand better what might be happening in supervised learning. Again, we don't have any evidence for this, but maybe this is just something else to throw in there. So yeah, that's about it. Thank you so much. And we'd be happy to take questions now.
Great, thanks. So we'll all applaud towards the end. Let me, not exactly a question. I thought the talk was very clear. Let me try to say it in my own way, and you can tell me if I got the idea. So usually in improving these generalization bounds, if you were comparing the training set, most expectations comparing the training set in the whole population, it's just statistics. It's just the same up to 1 over square root of n. And the problem is that now we're comparing something where the model depends on the training set. And so everything is conditioned on that. And now basically what you're saying is, let's grant that the model is such that some big piece of it doesn't depend on the training set and some other piece of it does depend on the training set, and let's just split it up.
Yeah, specifically, if it doesn't depend on the labels, then in some sense, you can still expect good properties from the initial part that is complicated. And if you only introduce labels towards the end, then in some sense, you're protected in what you're going to learn.
Yeah.
So let me just say that, I mean, the thing that you have to be a little bit worried about, or just make sure that you're aware of, is that we are computationally splitting up the parts to the data and the labels, but statistically, we are not really splitting it up, because statistically, likely the labels are completely determined by the data. There is no statistical, there is no additional entropy in the labels beyond the data. So that's why basically we are not able to use kind of off-the-shelf statistical, so that's why we cannot simply kind of use off-the-shelf, and we need to talk about things like rationality. So that's...
Okay, I see a question in the chat. Eric, would you like to ask it? Or maybe you're after Yang Zhang.
Yeah, so the question is, if you change the representation in the first stage, depending on the classifier performance, and no, we don't do that. So we keep the representation fixed, and we only train the simple classifier afterwards without changing the representation.
Does that answer the question? I guess so. Eric, would you like to ask yours?
Sure. I was just wondering if the bounds on generalization gap, you showed the final slide that they're bounds, but they even trend the right way, sort of. And so is that something that you could either theoretically or more likely experimentally say that I can therefore use the test set performance as a proxy, training set performance as a proxy for test set inside of an optimization loop over some hyperparameter that wasn't part of the training procedure?
Maybe not as direct. My intuition is that it would still be hard to kind of write out these additional terms that we have in the bound. So I guess what you're asking is if you could have train accuracy plus this bound as something that you can optimize. But my intuition is that there's things like rationality that might change a lot depending on how you optimize. But yeah, I'm not sure if.
But it could be directly, I mean, maybe the question is also like just directly, if you just try to optimize train performance, train accuracy on its own, I don't know if we will be able to prove anything about it, but it's an interesting experiment to run. It could be the case that there is still room, as long as the amount of information in these hyperparameters, you don't have too many of these parameters, it's quite possible that that the train performance, if you try to find the parameters that minimize train performance, they would also minimize test performance. But it's not some, I don't think we know how to prove that, and we haven't tried it. It's a nice experiment to run.
I mean, another way to ask the question would be to say, if you're, again, a practitioner trying to optimize, should you do some noisy experiments too and feed that into your optimization in this way?
Yeah, that could be something to check. Yeah, for instance, like if you this, for instance, would tell you that if you have a very complicated classifier at the end, then you probably risk overfitting and having poor generalization. Although it still depends on the entropy, which is not exactly easy to write out, but it does give some intuition that you shouldn't have something very complicated at the end.
And that effective complexity might depend on hyperparameters.
Yeah.
Okay. More questions?
Yeah, I have a question. I think this is kind of similar to Michael's original question and Boaz's response, but so I guess you can't use classical statistical learning bounds in this context because effectively the basis functions that you learn, the representation that you learn is going to be data dependent. So you can't just apply some uniform law of large numbers. However, if you just kind of forgot about that, then you would have a linear predictor in some high dimensional space, and you'd have some bound that's like given by the Rademacher complexity of this linear class of functions. And of course that bound would be incorrect, but are the numerical values that your correct bound predicts kind of comparable to what you would get by applying one of these linear classifier bounds?
Yeah, that's a good question. We didn't actually use the numbers directly. We do talk about like the mathematical difficulty in directly using, let's say, Rademacher complexity of the simple classifier, because in some sense, it's if you have this a complicated representation, you don't know if your train and test are coming from the same distribution anymore, which is what the condition would be if you wanted to just apply Rademacher. Yeah, but it's a good question. What would happen if you directly just pick them out and apply them and assume that the representation is somehow doing something that's well behaved, and that's fine. Yeah.
I think it's a very good question. Like to see if the gaps, if the numbers you actually get are the same, that if you did the heuristic that that things are completely independent. I'm guessing that there would be some gap, but it would be correlated. But I don't know.
Right. Okay. Interesting. Thanks.
I mean, to add to that, like, so the entropy bound that you have, isn't that like, if for binary classification, isn't that upper bounded in terms of VC dimension? Because like by Sauer's lemma, there are only n to the d functions, and the entropy is at most log of that.
I don't know particular theorem, but I would guess that it should be upper bounded by VC dimension, like if it's just the entropy, but yeah, I'm not sure about the particular theorem.
I see.
And I see there's also like a question by Kirk in the chat. So yeah, I guess if I can also read it out. Like so it was asked whether the notion of robustness we use mostly as a diagnostic tool and not as a true measure of the robustness of the classifier. So I think it's both true and false in the sense that yeah, it is only a mental experiment. Like we use only robustness to analyze the generalization gap, but it is actually related to notions of robustness that people have looked at. So I mean, I think it's not exactly because it's kind of robustness of the training rather than robustness with respect to the test, but I think it's I mean, it's not unrelated. We have, like in the paper, we do mention some references for robustness, so it's not completely unrelated to other. I mean, this is sometimes known as stability, and maybe Yamini remembers there are some other names that people have used.
I think people also call it noise tolerance, but I think one crucial difference is that they measure the performance on test, whereas we're talking about how much the train would degrade. But it feels like they should be related.
More questions? If not, well, let's thank Boaz and Yamini for an excellent talk. I'll unmute and clap if you like, or you can regard, so very good. So next week we'll be having Florent Kurzakala from the École Normale at the same time, same station. So I look forward to seeing you all there. Thanks again.
Thank you very much.
Thank you for having us.
Thank you.